Hey guys, just wanted to give you a couple ideas for the practice questions for number three. There's of course like a couple different ways to do this question because for this question we use the axiom of choice. So if you want, you can also try doing this question using either the well-ordering principle or Zoran's lemma, and it can kind of be good practice or kind of be interesting to see the difference between those different proofs. Okay, but you don't have to. Anyways, in this proof we're going to use the axiom of choice. Okay, so that means we're going to assume, so what is our situation? Oh yeah, let me mention one more thing. Our situation is we have supposed that we have a set whose cardinality is bigger than any given natural number. And we have to prove that the cardinality of the natural numbers is less than or equal to the cardinality of A. In other words, we want an injective function from the natural numbers to A. In the statement of this question on the practice questions, actually I incorrectly put a strict less than, which is wrong. The natural numbers themselves satisfy this property if I replace A with a natural number, so we can't prove that a strict less than. Okay. Anyways, okay, with that correction, we're going to be using the axiom of choice. So that means we're going to assume that we have a choice function, we'll call it capital F, choice function for the power set of A, in other words, the set of all subsets of A. This is a function which takes any subset of A, and any non-empty subset of A, and assigns an element of that subset. It chooses an element of that subset. So you have a choice function. This is what we get by assuming the axiom of choice. Okay. And now we're going to use the recursion theorem. And so that means I need a set, and I need a function from the Cartesian product of that set and natural numbers to that set. Okay, so my set is going to be the set of finite sequences which are one-to-one, so that means the domain of my sequence is a natural number, and the range is a subset of A, and my sequences I'm going to assume that they're going to be one-to-one. Okay, and this is my set A that I'm going to apply the recursion theorem to. And you can kind of think of roughly what we're trying to do. Okay, I don't have much room here because I've used it all up, but roughly what we want to do is the following. We want to construct a function like this. We want to choose maybe A0 to be just whatever the choice function gives in A. So apply the choice function to all of A, and call that A0. I'm going to call A of 1 to be to choose anything except for A0. Okay, and we choose A2 to be, use the choice function to choose anything, except don't choose A1 or A0 or A1, and so on. Okay, and that is our motivation behind constructing our function G. Of course, okay, so we're thinking of this A0, A1, A2, these are going to be sequences. Okay, and for G, I want to take a sequence and a natural number and find the image of the sequence in A and choose anything that's not in the image by the choice function, right? So what do we do? Well, I have how do I define G? I take any sequence. The sequence has the domain of that sequence is a natural number. Okay, now look at the image of that sequence. That's a subset of A. Okay, or the range, I should say. So look at the range of that sequence. Take the complement of the range. Apply my choice function to that, and make up a new function whose value at n is just the choice function evaluated at the complement of the range of my previous function, and for all the things less than n, I'll just define it the same as the old function. Okay, and this is what we're doing, right? So what this rule says is that if I'm given a sequence A0, A1, A2, I define A3. Well, I look at the complement in A of A0, A1, A2, use the choice function on that and call that A3, and my new sequence becomes A0, A1, A2, A3. Okay. So that is how I define G. And now, in order to apply recursion theorem, we need like kind of an initial element, and that is going to be just my whatever the choice function gives for all of A. Okay. Now we apply the recursion theorem. That gives us a function from the natural numbers to this set of finite sequences. Okay, so okay. Right, so here's some things which we should check. Anyways, we should check that the domain of f prime is a natural number. Yes, it is. We should check that f prime is 1 to 1. Well, that's because f is 1 to 1, and the way we define f prime is that like f prime of n is different from all the previous ones. So that kind of guarantees that f prime is 1 to 1. And finally, the only reason this works is because G is well defined, because if f is a finite sequence from a natural number n to a, because the cardinality of n is less than the cardinality of a, this set a minus the range of f, the complement of the range of f, is always non-empty. If it was empty, well, then we would know that a and n have equal cardinality, which is not. Okay, so we apply the recursion theorem now. That means there exists a function at h going from, h goes from the natural numbers to the set of all finite sequences. Okay, and h of 0 is just the sequence which sends 0 to whatever choice element. H of n plus 1 is just defined to be if I have the nth term of the sequence, I just kind of add on to it by defining G. Okay, so that defines like a sequence of sequences, but each sequence like has the property that here's h of 0 is the sequence a0. H of 1 is the sequence a0, a1. H of 2 is the sequence a0, a1, a2, and on and on. So each sequence is like adding on one term to the previous sequence, and now just take the union of all of them. Well, like if you remember, like the union of functions is a function under a certain hypothesis, which are satisfied for this. Okay, so you take the union of all the functions, and now you get that essentially what you do is you just look at a0, a1, like the sequence going to infinity, and notice that you have an injective function from the natural numbers to a. In other words, the natural numbers have or if cardinality less than or equal to a, and that's the end. Okay, so I hope you'll forgive me for skipping over a couple details. Okay, so I hope that you can also try also Soren's lemma and the well-ordering principle if you want. In a way, like you can kind of see like we're proving that we're kind of like this is like kind of like proving the well-ordering principle, but like some weak version of it. But okay. Thank you for watching.